A gas dehydration unit operates on the principle of absorption through a cyclical process. The process utilizes glycol to absorb water from the gas in a column before being regenerated or removing the absorbed water by higher concentrations with a heat source. Then, this process is repeated. Absorption of water in a dehydration contactor is enhanced by operating at a higher pressure, low temperature, and having column internals with a large surface area for contact of the gas with the glycol. The chimney tray, or deflection plate, is located at the bottom of the contactor and has two functional features. First, it acts as a deflection plate, preventing the incoming gas from directly hitting the bottom tray in the contactor. Operation ramp-up of production is often very fast, and without the deflection plate, the gas velocity could disturb the internal trays or packing. Secondly, it holds the rich glycol, maintaining a constant liquid level. There are many different designs for chimney trays, from rounded, outfitted with caps, or resembling an exhaust pipe. The following is a computational fluid dynamic, or CFD graphic, of a low temperature separator that shows a difference between fluid velocity at 2 meters per second and 5 meters per second. As you can see between the two graphics, at a lower velocity, there is a clear separation between the phases by the time it reaches the weir. Whereas with a higher velocity, there is still mixing in the liquid phase. This means, at lower velocities, the separation efficiency is higher, and at higher velocities, there is inadequate residence time to ensure proper separation of the glycol, water, and hydrocarbon emulsion. There are typically two identifiable symptoms of separation issues in the LTS. One is that the process is not producing enough NGL as predicted by the simulation, for the NGL ends up in the glycol phase and is flashing out in the flash drum, and is not being recovered as a product. In a two-vessel LTS configuration, liquids leaving the first vessel are routed to the second vessel, where the fluids are sometimes warmed to aid in the separation of the glycol-water phase from the hydrocarbon phase. Having a second separator provides greater liquid residence time, which reduces liquid carryover or carry-under, like glycol to the stabilizer or hydrocarbons to the regeneration loop. A gravity-separated glycol phase on the bottom will flow to the regenerator section. Regardless of the type of amine being used, the ultimate goal for H2S removal is good mass transfer. Every kilogram of H2S entering the contactor as a gas must leave as a liquid with the rich amine. This mass transfer occurs in a three-step process. The first step is gas phase diffusion. The gas enters the contactor and meets with the liquid amine as well as the tower internals. This causes a slight pressure drop, which forces the gas to expand. As the gas expands through the liquid amine, this initiates the second step, liquid phase diffusion. The amine and gas mix together and trigger step 3, the chemical reaction. The H2S and CO2 bond with the amine immediately, as acids are attracted to bases, and amine is a strong base. The condenser responsible for cooling and condensing the sulfur vapor to liquid, and the knockout responsible for removing the liquid sulfur from the process gas, were often built as two separate vessels. In almost all modern designs, however, the condensing section and the knockout section are now located back-to-back inside a single vessel. Thermal incinerators begin by burning fuel gas with excess air. The tail gas from the sulfur plant enters just downstream of this fuel gas burner, and the combination of high temperature and excess air results in the combustion of the sulfur species present in the tail gas stream to SO2.